For years, the golden rule of AI image generation has been brutally simple. If you want better quality, you just need more parameters. Bigger models, more compute, higher costs. But that approach is hitting a hard wall. Open-source generators are now scaling to 20, 30, even 80 billion parameters. The quality is undeniable, but training, fine-tuning, and even running these models has become a luxury most researchers and creators simply can't afford. What if the real bottleneck isn't the number of parameters, but how we architect the entire pipeline? Researchers at Microsoft just published a paper that completely flips that scaling script. They've introduced Mage-Flow, a compact 4 billion parameter model family that handles both text-to-image generation and instruction-based editing. And it doesn't just compete with larger models, it matches or outperforms them. The secret isn't in adding more layers. It's in a tightly co-designed system, where the tokenizer, backbone, and training infrastructure all work in lockstep. Let's start with how the model actually processes images. Every modern diffusion pipeline relies on a variational autoencoder, or VAE, to compress raw pixels into a lower dimensional latent space before the main network touches them. The problem? Traditional tokenizers are notoriously slow at high resolutions. Encoding and decoding can consume a massive portion of your total generation time, especially when you're dealing with multi-step compression and reconstruction. Mage-Flow replaces that bottleneck with Mage-VAE. Instead of running dozens of slow, iterative compression steps, it uses a single-step diffusion process to both encode and decode images. It's trained with a specialized regularization technique that keeps the latent representation tightly aligned with high-fidelity visual standards. The result is a tokenizer that preserves sharp textures and fine details while cutting computation time by more than 10 times. Once the image is in latent space, it moves to the backbone, a 4 billion parameter diffusion transformer. Most models are trained on fixed aspect ratio buckets, meaning they learn specific resolutions and shapes in isolation. When you ask for an image outside those predefined boxes, quality degrades, especially at the edges. Mage-Flow trains natively at full resolution. It packs images of completely different sizes and aspect ratios into a single training batch, forcing the model to learn spatial flexibility directly. This means it can generate standard squares, tall portraits, or ultra-wide banners without needing separate checkpoints, and it maintains structural integrity and detail across the entire frame. But architecture alone doesn't make a system practical at scale. The team also overhauled the underlying software stack. By fusing repetitive tensor operations into custom CUDA kernels, they drastically reduced memory bandwidth bottlenecks and training overhead. This isn't just a theoretical win. System-level tuning like this boosted training throughput by roughly 2.5 times, which means large-scale experimentation is actually feasible on standard consumer or prosumer GPUs. To make the model actually useful in real workflows, they applied targeted post-training techniques. First, they aligned the base model with human preferences using a method called Diffusion-NFT. This fine-tunes the generator directly against feedback for prompt adherence, aesthetic quality, and text rendering accuracy. Then they tackled inference speed through distillation. Standard diffusion models require dozens of iterative denoising steps to clean up a noisy latent and produce a final image. Mage-Flow's distilled variant, dubbed Turbo, compresses that process into just 4 steps. The distillation process preserves the core generative capabilities of the larger model while dramatically cutting latency. The numbers back it up. Across standard generation and editing benchmarks, Mage-Flow consistently matches or exceeds much larger open-source systems. But the real breakthrough is efficiency. At a standard 1024 by 1024 resolution, the Turbo variant generates an image in under half a second and edits one in just over a second. All of this runs on a single GPU with a memory footprint of just 18 to 20 gigabytes. It handles complex instruction-based edits like object swapping, style transfer, lighting adjustments, and background removal while keeping the rest of the scene perfectly intact. It also tackles one of the hardest problems in generative AI, text rendering. The model produces legible, correctly spelled English and Chinese characters on packaging, posters, and signage, avoiding the garbled lettering that plagues most competitors. And when fine-tuned for technical tasks, it accurately draws neural network diagrams, routes directional arrows, and renders mathematical notation with structural precision that rivals much larger specialized models. What does this actually mean for the field? It proves that architectural efficiency and targeted training strategies can outperform brute force parameter scaling. We don't need ever larger models that require data center clusters and massive energy budgets to run. By co-designing the tokenizer, the backbone, and the inference pipeline as a single unified system, Mage-Flow demonstrates that compact models can deliver professional-grade generation and editing. The era of unnecessary bloat is fading. The next generation of generative AI isn't about how many parameters you can throw at a problem. It's about how intelligently you solve it. And that shift is exactly what's going to make powerful AI tools accessible, deployable, and actually useful for researchers and creators everywhere.